So let me make Zhe the speaker now. Presenter. Great. Zhe, go ahead and share your screen. The next talk is by Dr. Zhe Zhang on Ray as the unified compute substrate for machine learning applications, basically the Ray machine learning platform. It's my pleasure to introduce Dr. Zhe Zhang. He leads the open source engineering of the Ray project at Anyscale Incorporated. Before that, he was a senior engineering manager with LinkedIn, managing the big data and AI computing infrastructure team that is basically providing a lot of Hadoop, Spark, and TensorFlow as services. Zhe has been working in the open source community, and he has been dedicated into the open source community for a long time. He is a PMC member of Apache Hadoop. He led the design and implementation of erasure coding in HDFS and developed that at LinkedIn as well, right? So it's my pleasure to welcome Zhe to Scalable 2021, and Zhe, take it away.
Thank you so much, Jerome. Thank you, everyone. Good afternoon. Thank you for dialing in. I'm really glad to see many former colleagues at IBM Research. Very excited about this. Today I'm very excited to talk about the emerging pattern of using Ray as the unified compute substrate for machine learning platforms and applications. So first, as Jerome already gave an introduction. Basically currently I lead open source engineering at Anyscale, and the company is around this open source project called Ray. And here is the structure of my talk today. First, I'll start with the motivation and history of Ray, why kind of we developed this system, and then I'll go into the Ray architecture, use cases, and a little bit of deep dive into one particular domain of tuning the hyperparameters for machine learning. So first I'll start with the motivation. So I think, yes, to put it simply, the team at UC Berkeley started the Ray project around the belief that the future of computing is to be distributed. So distributed system is definitely not a new concept. As early as the 1970s, there's the ARPA network, and going into the 90s, there's the huge increase of the adoption of HPC, right? So in simulation and different other scientific environments, I'm pretty sure folks at IBM Research are very familiar with this. And going into the 1990s, there's the emergence of web. For example, Amazon, they have this very popular framework of using a client and server and serve the entire world. And then in the 2000s, there's the emergence of big data, right? So powering analytics, artificial intelligence. So, but with all these developments, at today, distributed computing is still an exception, not the norm. So as we can see, today, developing distributed applications still requires a lot of expertise. You have to be an expert in this domain. And people who have this expertise is a small percentage of all the developers, right? And to make the problem worse, from the education side, very few universities teach distributed computing as their standard curriculum. In comparison, you can think about operating system, database, that's pretty much a standard. Right, so, our prediction is that this trend will change. So distributed computing will become the norm, not the exception. So what's different this time around? We have summarized, three basic reasons. One is the rise of deep learning, which is the theme of this workshop. So that's great. So increasing adoption of deep learning. That's the first reason. The second reason summarized is the end of the Moore's law from the hardware side. And then from the application side, we are already seeing the trend that applications are becoming AI-centric. Almost every application has some element of AI in it. So first, the deep learning, the demand for deep learning. So this is from OpenAI. So the x-axis is the time horizon. The y-axis is the demand for computation in terms of petaflops per day. And notice that this is actually a log scale. So as you can see, the growth is really fast. So every 18 months, the compute demand for state-of-the-art deep learning models grows 35x. In contrast, I'm also drawing in this chart the growth of a single CPU core processing power. The growth is much slower than the demand for deep learning, and the gap is huge. Right. To make this problem more interesting, if you look at today's applications, right, either it's HPC, big data, microservices, they all need some flavor of AI. Take big data, for example, right? So with big data, there's a lot of logs generated, there's feature data generated, right? So all this is very closely to AI and microservices, right? Today's services is enhanced a lot by AI, right? So AI applications are becoming AI-centric, right? So with this huge demand for deep learning and the slower growth of hardware and the AI apps becoming AI-centric, so it's basically an inevitable trend that applications need to become distributed. We need to leverage and harvest the power of multiple machines or quote-unquote clusters. On the other hand, developing distributed applications is extremely hard. So there's no general solution for end-to-end AI applications, right? So if you're developing an HPC application, you might use things like MPI. If you're developing big data, the standards are Hadoop, Spark, Kafka, Flink, and for deep learning, you have TensorFlow, PyTorch, Harvard. Microservices, you might choose Go, but there's no central platform for you to kind of develop all these application scenarios in a more unified way. So what do people do in this situation? So people are currently making a trade-off between these two dimensions. One is how general this framework or API is. Another is how easy it is to develop based on this framework for your application. For example, right on one end of the spectrum, some people choose to develop from very low-level APIs, directly using Kubernetes and Docker to start up containers, and directly writing the code for single containers and using RPC to handcraft the communication between containers. On the other, so this solution is definitely very general. You can basically do everything from containers and RPCs. But it's very difficult to develop. You need to manage many things yourself, fault tolerance, state management. And on the other end of the spectrum, some people choose to have easy development. People can use serverless. For example, on cloud vendors, you can use Lambda and Google Cloud Run, and IBM Cloud also has a serverless offering. So this is very easy development. You just develop the code on your local business logic, and the framework takes care of state management and fault tolerance and other considerations. But it's also very limited. Typically, it's specific to one cloud, and typically is for stateless logic, and there's no special hardware support like GPUs, TPUs, and typically the runtime is limited to something like 15 minutes. And some people choose a middle ground. They can stick together existing frameworks, which is somewhat harder to develop than serverless, and somewhat less general than container plus RPC. So to simply put, Ray tries to achieve both these two benefits, being very general and also very easy to develop. So because of these strong attributes, Ray is having very good trajectory of growth. So this here we're kind of carving the different trajectory in terms of GitHub stars of different popular open source projects. As you can see, in terms of absolute growth, Ray is faster than popular projects like Dask, MLflow, Kafka, and even Spark. And in terms of contributors, definitely also faster than linear growth. So in the next part, let me dive into the architecture of Ray. So after the motivation part, you might wonder what is under the hood so that Ray can achieve this benefit of both being very general and easy to develop. So I'll start with the simplest example. So here I'm showing it's not about Ray yet. So it's the most simple vanilla Python code. It will define a function. The function is only sleeping for 1 second, and in the main part of the function, in the main part of the code, you call this function 8 times, and you collect the results. Right. So Ray has the power to basically, with very simple modifications, basically in the function, you add one Python decorator at read.remote. And in any other part of the code, you can call this function as a remote task to be scheduled on a cluster. So with this simple modification, when you do this function will basically be run in parallel 8 times, and you can harness the power of multiple cores on a single laptop or a cluster. So a slightly more complex example of using reactors. So a very common pattern is to have a supervisor actor, basically a process, right? For example, scan through the files in a directory and assign different tasks to different worker actors. So as you can see, the code is very simple. It's not too much different from vanilla Python code. You just start a supervisor actor. Its main responsibility is to scan through the directory for files and determine what worker actors to spin. And the worker actors does simple tasks. I think I want to emphasize the very powerful nature of rescheduling. So basically, you can schedule actors from actors. This is what we call the nested parallelism. And to do that, it's very simple. So in one remote actor, you can just do another actor.remote. So you're doing this nested scheduling just by this simple code. So actors are extremely powerful. They allow you to package your Python class, your business logic, and instantiate that business logic as a microservice, which can interact with other services in the most flexible way. So to put it simply, Ray has these the upper level APIs, the task, actor, and object. They map to the functions and the classes and objects in regular programming language. And to support these APIs, Ray has this autoscaler which will launch Ray nodes in different environments. We call it autoscaler. So you can run Ray on the laptop, local cluster, Kubernetes, and different cloud vendors. So now let me dive a little bit deeper and talk about the different components in a typical Ray cluster. In a Ray cluster, so every Ray cluster is composed with a collection of Ray nodes. And every node runs these different processes. There's a special process called relet. Relet controls other processes on the Ray node. So the relet also is always responsible for scheduling. So from any node, the relet can run a scheduler logic and spin other tasks and actors. And the relet also is responsible for managing part of the local memory and contribute to a distributed object store. That means you can put an object in anywhere in the cluster and get an object from anywhere else in the cluster. So there's only one special node in the cluster, which we call the head node. In addition to the relet and worker processes, this head node also runs the global control store. it controls the global level metadata. And the head node typically also runs the driver program, which is the starting point of any program that the user might interact with the Rig cluster. So yeah, diving further a little bit deeper. So the reason Rig can provide these simple and general APIs, task and actor and object, is that Rig is hiding the complexity under the hood. So one of the key complexities that Rig is hiding in the system is called ownership. So in the leftmost part, I'm showing a program. So we define a function called B, which just returns, and we define a function A, which further calls B. And then in the main part of the code, we put an object into the Rig object store, and then we invoke the function A, right? And in the middle part, this is how Rig translates this program into a graph of dependencies and tasks. So basically, the main part of the code, or the driver, owns or starts the object X and the function A and object Y, right? And as you can see, function A in turn calls into function B, and function B result in object Z. So that means the driver is the owner of A and X and Y, and worker A is owner of B and Z. And as the owner, the process is responsible for keeping the metadata of the object being owned. For example, worker A now is responsible for maintaining the information of where is worker B and where is drop object Z. Yeah, this part, I'm happy to answer any questions at the end. So yeah, so based on these basic APIs, task, actors, and objects, people have built a variety of different libraries on top of Rig. On the left side, we have the native libraries on Rig. That's basically started and maintained by the Rig team. We have this RL-lib library, which does reinforcement learning. It's a leading solution for RL. And we have another library called RigTune. It's for tuning hyperparameters in doing ML training. And we have Reserve, which will serve ML models after the training. And we have a very large ecosystem of third-party libraries. For example, we have this integration with this very popular deep learning framework called Harvard. And we also have good integration with natural language libraries like Spacey, Hugging Face, and data processing libraries like Dask, and metadata libraries like weight and bias. So, in the future, our vision is Rig is to become the go-to framework if you want to develop libraries that will eventually require heavy computing and distributed system support. So now I want to dive into this use case of using Rig as the substrate for machine learning platform. So I will use the Uber as the motivating example in this topic. So many of you might have already read about Uber's machine learning platform called Michelangelo. It's one of the earliest end-to-end machine learning platform in the industry. There's a very popular blog post from Uber describing the usage and architecture. So this slide describes the state of art for a machine learning workflow on Michelangelo. This is before they integrated with Rig. So Uber has another open source project called Peloton. It's similar to Kubernetes. It's Uber's internal resource management layer. And on top of that, they run different kind of machine learning workloads. For deep learning, Uber use Horvath to support both PyTorch and TensorFlow deep learning. And for classic machine learning, Uber mostly rely on this library called XGBoost. And Uber also has code-free AutoML. There's another open source project called Ludwig. And all these runs on this resource management layer called Peloton. as you can imagine, doing machine learning requires typically these different steps. You need to pre-process the data, you need to do the model training, and you need to do the evaluation. And with these different steps, what Uber Michelangelo team used to do is to use external orchestration engine like Airflow and stitch them together. And between these steps, they use external storage, for example, storing the data in Parquet and HDFS. So the overhead is pretty high, right, in materializing the data after the pre-processing and loading the data before training. So yeah, so here there's a summary of the drawbacks of doing machine learning in separate steps, right? First, for each system, it requires a separate team. It's very expensive to maintain because there's a separate team who is familiar with the Spark environment, another separate team who's familiar with the deep learning environment, including GPUs, right? And another team who is familiar with online serving. And adding a new system is very expensive. If you think about the scenario of currently you're doing TensorFlow, but your company want to evaluate PyTorch, so even adding the support to the underlying resource management layer is expensive. And interacting between these different steps requires the external orchestration engine and materializing the data in external storage. So here comes the reintegration. So re is providing just the right level of abstraction, right, for this problem. So on top of this resource scheduler peloton, in addition, if you have a relayer, then integrating these different libraries and steps is basically it's very simple. It's much simpler. Is on the level of code imports. So here I illustrate. Right, so yeah, Re basically simplifies this deployment, and it's much easier to add different environments, and is making the new frameworks much easier to deploy. So, and to illustrate that, here's an architecture of the machine learning platform after the reintegration. As you can see, we have this box at the top, which is a recluster. It's a single recluster. And within a single recluster, you can do all these different steps. You can do pre-processing using your favorite tool. Could be Spark, could be Dask. And then the data is seamlessly transferred to deep learning training. You can use TensorFlow, PyTorch, and again, evaluation again is done on Ray. So the need for an external orchestration engine is eliminated. So everything is a single Python code. With this train.py, this single Python code, you can do all these steps. That means the barrier of entry is much lower. As a machine learning engineer, you can basically deal with this single Python code. You can do local debugging, and you can do unit tests before deployment. And the data transfer between different steps is much easier. You can use Re's object store and treat these intermediate data set as variables. They are becoming programmable. Yeah, citing some keynotes, key quotes from the blog post we published with the Uber team. So we believe Ray will continue to play increasingly important role in this domain of production machine learning, and will eventually become the common infrastructure for standardized production machine learning. And the key benefits include combining the pre-processing, distributed training, and hyperparameter search in a single platform. Another example is more combining the batch streaming and online serving from Ant Group. So here it highlights the benefit of using Ray in making the development much easier. So if you think about a scenario of requiring batch processing, stream processing, and online serving, without Ray, the development team need to get familiar with different tools. But with Ray, the complexity is reduced significantly. And last part, I want to dive into a specific scenario of doing machine learning on Ray, namely tuning hyperparameters. This is a very interesting domain because if you think about hyperparameter tuning, it really requires searching through a space of different hyperparameters for your model training. And in doing that, there are different algorithms, right? You can search in the hyperparameter space in different ways. So it requires very flexible pluggability. And in doing the actual training for each run, we need another layer of pluggability for different frameworks. TensorFlow, PyTorch, Keras, MXNet. So really exactly provide these nested pluggability and nested parallelism. So here's a code example of how actually to use it. The first step, definitely set up the recluster. And then it's as simple as calling tune with a predefined training function. By doing that, you can fully leverage the power of Ray in GPU and elastic training, which means you can, for example, leverage spot instances on the cloud, right? And right. So and Ray can with retune you can plug in your favorite tuning algorithm from these different algorithms, from these different libraries. So the first step of using retune is to define this training function, each individual training function. That's very similar to doing machine learning. The regular training function, you define your loss function, and the key part is to report the loss function back to the tuning layer. And then it's about calling this training function from the retune API. And retune can basically react to this reported loss function and search in this vast space of hyperparameters. And here's an architecture to illustrate how this works. As you can see, in each individual training is a distributed computation, right? So it was being different workers using either parameter server architecture or peer-to-peer architecture, but retune also orchestrates these different distributed training and decide what is the next set of distribution training to run. So these two levels of parallelism or two levels of distributed computing is extremely difficult to program without a general framework like Ray. So with retune, you can integrate with deep learning like Harvard or using classic machine learning like XGBoost. Here is an example to integrate retune with Harvard. So if you remember, it starts with defining a training function, and in this example, we're defining the training function in Harvard. And then you basically feed this training function into retune. And yeah, so with 5 minutes left, here's my last slide. So Ray is a general framework for people to develop distributed applications, and up to this point is used a lot in machine learning, in particular deep learning applications. So yeah, please definitely give it a try. And we have this upcoming resummit, and also yeah, look at our documentation, and we also have office hours. Thank you. I'm happy to take any questions.
Thank you, Zhe, and it was a great presentation. Are there any questions? Just unmute yourself and ask your question.
Yes, I have a question. Thank you so much for this excellent presentation and overview about Ray. Since Ray runs on top of these, systems like Kubernetes and the Uber system that you mentioned, does it introduce any overhead in terms of running and deploying in machine systems end to end? Have you measured, any overhead involved with the deploying Ray?
Yeah, great question. Yeah, we haven't observed too much overhead because Ray can also directly run on machines. So if you have bare metal machines, you can always start relets, and they can compose a Ray cluster. Up to this point, deploying on Kubernetes has been the most popular option, and we haven't observed too much overhead compared with the bare metal cluster setup. It's basically down to the overhead of running a Docker container versus directly running on the OS.
Mm-hmm.
Yeah, this should be, it depends on usage scenario. I think in really latency sensitive applications like serving a machine learning model, that might be a consideration. For batch workloads, it should be negligible.
Thank you. And another question I have, is there like any built-in support for debugging or errors, when things fail in Ray or underlying layers?
Great question. I think this is actually a strength of Ray because in debugging a distributed application could be extremely hard. But Ray presents this illusion that this is a coherent vanilla application. Ray has this distributed debugger. If you think about it, if you write a distributed application in Ray, the communication between two processes, even if they're on different nodes, is regular function calls, right? It's basically class A calls into a method in class B, and Ray's distributed debugger allows you to debug it as if it's a single node program. You can have breakpoints of these regular function calls, even if under the hood is RPC calls. But if you're developing the distributed application from containers and RPCs, as you can imagine, the trees or the debugging breakpoint will not work.
Yeah, it's very complex.
Yeah, we do have a distributed debugger, and we recently added open telemetry-based tracing as well.
Thank you.
Thank you. Great questions.
Any more questions?
So I have one question. Hi, Z. So hi, how are you? So how
Actually,
does
hold on. Sorry to interrupt. I believe someone else was
oh,
raising.
sorry. Okay, but let them go ahead. Let them go ahead first. Yes.
James, would you like to ask a question, or I believe you were speaking?
No.
Okay, go ahead, Paljat. Sorry.
Okay, thanks. So can you tell me that how does Ray compare with like things like Kubeflow or Khatib and which also run over Kubernetes, right? And they also offer end-to-end ML pipeline composition. Even you can do hyperparameter tuning with Khatib, right? And you can they have support for different algorithms, right?
Yes, right. Yeah, Khatib is another hyperparameter tuning library. I think it's basically down to a chart I showed before about the trade-off of directly doing things with container APIs versus more general programming API. The architecture of Kubeflow is that the Kubeflow operator developer. So there's some developers, they are in charge of developing these operators, right? So I think Kubeflow started with TensorFlow. If there's a demand for PyTorch, then a team needs to develop the PyTorch operator. Is a Kubernetes CRD or operator. They need to the operator will allocate containers from Kubernetes, and they will be in charge of the communication between containers to support its distributed computing. I think to put it simply, doing the same thing on Ray will be much quicker to develop. Right. So yes, you can. Of course, you can do it on Kubernetes because it's container and RPC kind of abstraction. It achieved end goals, but I think the development cost is different.
The question.
Sorry. So is it fair to say that there will be there's a in the open source community there's a competition between both of them, or they are like they have a different support of base?
Yeah, I would say yeah, it's a very yeah, machine learning platform is growing very fast as an entire segment. Some people are yeah in orchestration. Yes, we have seen some users evaluating both. So right is for example, if a company has a very strong Kubernetes development and expertise already, then we have seen that they would prefer Kubeflow. If a company they have some knowledge existing in the company, then yeah, they would probably choose the reroute. But yeah, I wouldn't say they have they're operating on different level abstractions. So Kubeflow mostly solves the ML ops problem, and Ray solved a slightly lower level problem of developing these operators and distributed applications.
Thank you, Zhi. Okay, yes.
Thank you.
Great. Actually, I have a couple of questions, but we are out of time. So I'm going to synchronize with Zhe offline and ask those questions. Thanks a lot, Zhe, and it was a great talk. And thank you very much.
Thank you.
Yes,
Thank you. Thank you so much. Bye-bye.
Bye-bye.